and then you did a postdoc, if I remember correctly, in Reykjavik, and then in Göttingen, and now you're a lecturer at St. Andrews.
Yes.
Yeah. So, and he will be talking to us about exploring temporal graphs with frequent edges. Okay, go ahead.
Thank you. I think I got a much bigger introduction than the previous speaker. So I'm going to be talking, as George said, about exploration on temporal graphs with frequent edges. Again, like the previous speaker, this is not the name of the paper. It's a truncation of the name. That's the more interesting side of things. I'm going to start with my preliminaries, and I'm glad I did because I've used a very slightly different version of defining temporal graphs than the two ones that we got in the last talk. So probably for the best. Rather than defining it based on a labeling or based on just a series of distinct snapshots, I just use the notation of one singular vertex set and a list of sequential edge sets. I do this because I keep on using set notation throughout the rest of the paper or the rest of the talk. But in general, we have edge set EI represents the set of vertices that are active in time step I. I do not have any additional restrictions. We're allowed to have an edge active in one time step or three or every single time step. In fact, that's very important when it comes to them being active frequently. And I use the term underlying graph as the static graph which we get when we take the vertex set and the union of all of the edge sets. So just to give a little example, and again, we can actually see having multiple time steps with edges active. Here we have a vertex set 1 to 5 and edge sets 1, 2, 3, 4, and 5. And in this example, in each edge set, we have all of the edges incident to a given vertex active in one time step. So time step 1, all of the edges incident to vertex 1. Time step 4, all the vertices incident to number 4. Also, this just seems to have started working, and I don't know quite how that happened. I'm just lucky, I guess. So even though this wasn't the title, I'm actually going to start with defining regular edges because I think they're slightly easier to understand than frequent edges. An edge is regular, essentially, if it keeps on appearing in a regular fashion. It appears in, say, if it is 3 regular, it'll appear in time step t plus 3, t plus 6, and so on. Basically, we just keep on seeing it again and again with a nice regularity. A graph is R regular if every edge is itself R regular. One thing which is worth noting here, we can have it start in multiple time steps which are not uniformly distinct. So we could have a 3 regular edge that is active in time step 1 and in time step 3, even though 1 plus 3 does not quite equal 3 under at least most definitions of addition. That's still okay. It's still regular if it's like 1, 4, 7, and also 3, 6, 9, because we still know that we have this guarantee on the waiting time, and that if we arrive in one of these two sets of time steps, we're guaranteed still to have the edge active. So just to give a very simple example, the 3 regular graph, here we get time step 1, we have all of the vertices and all the edges in the pro active. Time step 2, we get all of the columns. Time step 3, we get the bottom set of edges. And then time step 4, we go right back to what we have in time step 1. And then time step 2, again, with these columns. And time step 6, we have the bottom row again. Yes?
Yeah, sorry. So 3 regular doesn't mean that it appears at t plus 3, t plus 6 only. It could appear more.
Yes.
You can guarantee that it appears really.
Yes, exactly.
Basically, guarantee that so if it appears at any time step, it will appear at least once before the time step of 3.
No.
No?
That is what we call frequent edges. So you actually managed to get right to the next definition. Regular is exactly that. Possibly also more, but it has to exactly be there. Frequent is that it appears at least once in the next f time steps. And we're going with the frequency of an edge, f of e, just the value f such that the edge is f of e frequent. The idea here is that, as we were saying, what we want is to say that the edge appears at least once in the next f time steps, but not necessarily with any regularity. And the goal here is that it means we have some bounds on how long we might have to wait before taking an edge, or transitioning along the edge if we're doing some exploration. And again, a graph is f frequent if every edge is f frequent. So to get an example of a graph with frequent edges, here we have a 2 frequent and 3 regular temporal graph. So firstly, to get the regularity, we can just see that copy and pasted the top row and the bottom row. So of course it's going to be 3 regular because we go exactly the same edge set is active in everything 3 time steps apart. But in terms of frequency, let's take the top edge. It's active in time step 1, it's active in time step 2, it's not active in time step 3, so we have to wait 1 time step, but then time step 4 we get it again. So we're never having to wait more than functionally 1 time step, which means it's active at least in any sequential pair of edge sets. And so 2 regular, but 3 regular, 2 frequent. The reason we want to focus on frequent rather than regular is that, of course, any R-regular temporal graph is R-frequent, but not necessarily the other way around. So if we get a good upper bound on the amount of time it takes to explore a F-frequent temporal graph, we get the same upper bound for F-regular. Conversely, if we have a lower bound on our regular temporal graphs, which isn't, don't think we have time to go into in this talk today, but if we do have a lower bound on our regular graphs, then we also get a lower bound on our frequent temporal graphs. Finally, I'm going to be the last of the preliminaries here is talking about temporal walks. So like a walk in a graph, temporal walk is a sequence of edges where we have that edge 1 has to end at the starting point of edge 2 and so on, as well as a ordered set of time steps such that, well, in this case, edge I is active in time step ti, and you're using a strict ordering, so T1 has to happen strictly before T2 and strictly before T3 and so on. In effect, our agent is only going to be allowed to move along 1 edge at each time step, and so we have a nice strict ordering of these. Given an agent following a temporal walk, we are going to say that if the agent is not moving at some time step, so if there's some time step between T1 and T2 that's not being used in our walk, we say that the agent is waiting. Basically, it's just sitting wherever it wants to next appear. So if we go back to this example of a regular graph, we can make a walk from V1 to V8 by first. In time step 1, we go from V1 to V2. Time step 2, we go from V2 to V6. Time step 3, V6 to V7. And now we're very, very close. By the time step 4, we have no outgoing edges, no edges connected to V7, so we're just going to have to sit there and wait. And time step 5, we can go backwards, but that's no good to us. And then finally, in time step 6, we're able to go from V7 to V8. So we say that in time steps 4 and 5, the agent is waiting at vertex V. A lot of algorithmic work on temporal graphs focuses on these ideas of reachability and exploration. Exploration, which is more relevant to this talk, is asking if there is some walk where we can visit every single vertex at least once. Okay. Yes, for those of you online, we had a lovely interlude by the iPad, asking to be think charged, but my German is not good enough for that. The optimization variant of the exploration question is asking what is the walk that ends at the earliest time step that explores the whole graph. So, moving on to the results. Firstly, is going to be that an F-frequent temporal graph can be explored in at most F times the 2 times the number of vertices minus 3 time steps. We're going to see this 2 number of vertices minus 3 come up a lot with slightly different things up front. The idea here, and it's going to seem a bit contrived, but we'll see in the next bit why, is that we just build a spanning tree on the underlying graph, and then any walk that can explore this tree will also thus explore the underlying graph. And we can find a walk that explores a tree very efficiently, and which requires at most 2 times the number of edges minus 1. So hence when we're getting this number of vertices minus 2 times the number of vertices minus 3 idea. Then we want to just convert this into a temporal walk. So what we do is that in the first set, We are sitting on our vertex and we want to move along the first edge in our walk on the underlying graph. And either the edge is active, which is great, and then we walk along and take one step, or the edge isn't active, in which case we're just going to be sitting there waiting until the edge becomes active. The key thing for our plane is that the edge is going to become active after, at most, f time steps. So we might be sitting there for a little bit, but we have a good bound on how long we're going to be waiting. In general, we say that the time step ti, so the time step at which we're transitioning along the ith edge in our walk, is going to be the first time step after ti minus 1, for which the edge I is active. But again, what we have is that we're never going to be waiting more than f time steps, just by the definition of frequency. So we have this bound that each time we're only waiting at most f time steps, and that gives us this upper bound on the exploration of f times whatever the path in the exploring the underlying graph is. But really, in most settings, we might have some ideas on the frequency, but the frequency isn't going to be uniform across the whole graph. A train might run once every hour, but the bus is running every 10 minutes. Some connections are going to be far more frequent than others. So what we want is to try and work out how long do we actually have to take if there is slightly less uniformity in the edges. Here we're going to be using an idea which I call the frequency-weighted graph. And this is just a static weighted graph where our weighting function maps from each edge the frequency of that edge. So if an edge is 10 frequent, the weight on the edge in this new graph is 10, and so on. Our claim here is that if we have a temporal graph, then it can be explored in 2 times f time steps, where capital F here is the weight, the minimum spanning tree on this graph. And this largely just follows the same idea as the previous theorem. We make this graph, we find a minimum weight spanning tree, we make a walk on this minimum weight spanning tree, and at each edge, we're going to be weighting at most the weight of the edge. So by just taking the sum of the weights, multiplying that by 2, because we might be going back and forth on each edge at least once, we get an exploration that requires at most 2 times the weight of the spanning tree. So this means that if we have 1 or 2 very infrequent edges, we don't actually necessarily have to wait that long. So if we take a more example here, we have this temporal graph. We're going to assume it's just repeating these 3 time steps over and over. And so it's here, here, here. Firstly, we make the weighted graph. So this edge is weight 3 because it only appears in 1 of 3 time steps. Whereas this edge has weight 1 because it appears in every single snapshot. I guess slightly mislabeled this one. Or rather, forgot to put the edge here and here, but otherwise, the idea is just that we take the edge, put a weight on it corresponding to how long we might have to wait. Find minimum weight spanning tree on this, and then we just make our exploration based on a walk on this tree. Technically, we want the minimum weight walk on the tree, of course, but it's much harder to make a really strong claim or a nice way of writing a theorem when you have to have 10 different definitions on it. So if we're saying starting here, we go take wait 1 step with this vertex, wait 1 step with this one, and then we're backtracking, and so on as we just go along the whole graph to our final vertex. Of course, we can generalize this right away to these regular graphs. So we can explore our regular graph in r times the 2 times number of vertices minus 3, and we can explore a graph in general in 2 times the r time steps, where this is the weight of the minimum spanning tree on what we call the regularity graph, which is just the frequency graph, but we weight it with the regularity rather than with the frequency. I'm just going to finish up with some motivating examples. The first one we have is what I call the sequential connection graph. The idea behind this kind of graph is that we have a rotating set of edges around each vertex, and we're only going to have 1 active each time step. So at time step 1, we might have edge 1, then time step 2, we have edge 2, and so on. The idea here is that we're simulating something maybe like a router, where we're not reading every single port at every single time step. We're actually just reading 1 port at a time, waiting to see what information comes in that port. Then we do some virus scanning or similar. And then before we send the message on to other vertices. And our claim here is going to be that we can actually do this quite quickly. We can actually explore these quite quickly. Because what we have is that each edge has a frequency of at most degree of the vertex in terms of a frequency of at most the degree of the vertex, which means that we actually only have to wait 4 times the number of edges in the graph. So we go to so rather than having to go through making the weighting, looking at the weighted spanning tree, in the same way as before, each vertex, each edge has a frequency of the most degree of the vertex. So the weight of the spanning tree is 2 times the number of edges. So we can do 2 times the weight of the spanning tree and 4 times the number of edges. That's the bigger and slightly more complicated result is on broadcast networks. So this is an idea which comes from distributed computing. In distributed computing, one of the models of communication is the broadcast model. In this model, at each time step, a vertex either sends a message to all of its neighbors or it doesn't say anything at all. So this means in the phrasing it in terms of our temporal graphs here, either we have every single outgoing edge from a vertex is active, or none are at all. We assume in this case that the directed graph is symmetric. So that means that for every outgoing edge, we have an incoming edge, with not necessarily with the same frequency, not necessarily active at the same time step. In fact, often not active at the same time step by our definition here. And what we want to, and this is something where it becomes much more prominent in these distributed settings, because we want to know if I have a message in this network, how long is it going to take to propagate across the whole network? And we have a couple of additional restrictions. Firstly, we're going to assume that no node is going to activate until every single one of its neighbors is also activated. So we're not going to activate it until it's heard back from all of its neighbors. The idea here is that we want to preserve some notion of synchronization across the graph. We don't want one vertex, one subgraph firing 1,000 messages without any indication that it has heard back from its neighbors. The second restriction, and this one is perhaps a bit more boring, we're assuming that we have at least one node active at each time step. There isn't really much point in exploring reachability problems when there's a time step where nothing happens at all. For tie breaking, we are going to assume that if two nodes send a message at the same time step, they assume that they know that they assume that they can go ahead with the next time step. So to give an example, we take this as our underlying graph. We use these green nodes to indicate vertices that are allowed to send a message, and blue nodes to indicate vertices that are sending a message. So the first time step, we have this node over here at the top of the left. All of its neighbors are going to hear something from it. And then on the right over here, we have this clique where they're all sending a message to each other. But then in the middle of the graph, we have this big gap where nobody is talking. In the next time step, and I'm now going to be using reds to highlight the vertices that aren't going to be allowed to send a message yet. This vertex at the top left, now it can't send any message because it's not heard anything from any of its neighbors. On the right, these three in the clique, they all heard a message in the previous time step from each other. So they're fine to send another message. But right at the edge of the clique, we have this red node, which, sure, it heard from three of its neighbors, but it's still missing a connection from one neighbor down there. And then we have these three nodes in the middle that are propagating out some more messages. Moving on to the next time step, now we're sending a bit more on the left-hand side, but this clique now is completely stuck. None of them are going to be able to send a message. Functionally, they're blocked by this node that is connecting the clique to the rest of the graph. Meanwhile, this slightly sparser area, we're still able to keep on sending messages because they don't have as many neighbors that they have to wait on. Now we're activating some of the last neighbors of this vertex on the left, and it's finally able to come alive and start sending messages. And we sent a lot of messages now in the middle, which means we're now in the state where we have a very empty graph. At this point, we only have this vertex here that's able to, this vertex here sending a message and very few neighbors. But once we send this message, we're able to invert all of those green nodes and get a large revitalization of the graph. Now we have basically everyone is able to send messages again. Our first theorem is that if we assume the graph is always connected, so that means that every time step, every vertex has some edge that's either incoming or outgoing from it that connects it to the graph. Essentially, if we strip away the direction of the graph, the new undirected graph becomes a single connected component. And our claim here is that if we have such a graph, the number of time steps it takes, essentially what we're saying is the frequency of each outgoing edge is at most small delta, where small delta is the degree, the minimum degree of any vertex in the underlying graph. The idea here is that at each time step, if we want the whole graph to be connected, a vertex is active in one time step, but it can't wait too long until it becomes active again. If it's active in time step t, then of course it has to be active in time step at most degree of the vertex plus t. Because I can wait for each of its neighbors around it to send a message, and so in each time step it gets one neighbor sending out a message, and then after all of those neighbors have sent a message, it's allowed to be active again. But of course, the frequency of those neighbors is also dependent upon their own degree. So if the neighbor view of vertex v is sending messages very frequently, then all of the edges around vertex v have to be activating as frequently. So it actually also has to be less than or equal to the degree of its neighbors. But then each of those neighbors has to be less than or equal to the degree of their neighbors, and so on. And so as we extrapolate across the whole graph, we end up in a state where each vertex has to be as active as whatever the lowest degree vertex is. Our second claim is that if we have a, without any claims on the connectivity of each time step, if we have any broadcast network, it can be explored in the diameter of the graph times the number of vertices times 2 times the number of vertices minus 3. So the frequency is the diameter of the graph multiplied by the number of vertices. Since I'm aware that we are running a little low on time, I'm not going to go into all of the gory details, but the basic idea is that if you imagine a path graph, so we have vertex 1, vertex 2, and so on in a nice straight line, we can really just force one vertex to have to wait at most d time O of diameter times the number of vertices time. By looking at furthest vertex, we activate that times step 1. Times step 2, we activate that vertices neighbor, and then we go back and activate it again. Then we jump forward to the neighbor, distance 2 from that vertex, we activate that, and we go backwards, and so on. Essentially, we just keep on looking. Firstly, furthest vertex is active, then all of its neighbors, then it again, then all of the distance 2, then the distance 1, and so on. We're back and forth until we get this rather up and down. So I'm just going to end with a couple of open problems. Firstly, can we get a better algorithm for exploring graphs with frequent edges? We do have a worst case bound, which gives us this lower bound of the size of the weight of the minimum weight spanning tree times 2 minus a small constant. But we believe that we can probably make a slightly stronger claim that there is a better algorithm for exploring it, especially when we have the frequency, a uniform frequency across the graph. The second one, which I'm interested in, is about the frequency of general broadcast networks. I conjecture that there probably is a slightly better bound on the frequency in general than the diameter times the number of vertices, but we still don't have a full proof of that. Thanks for listening. If anyone's interested, feel free to come up to me during the lunch or the breaks. I'm always happy to talk about more of these problems.
Questions?
Yep.
For the first result exploration, the lower and upper bounds, I didn't see it. Is there an assumption of connectedness for the chunk sets as well?
No, so in the original, just for those of you online, the question was about any assumptions on the connectedness on the original claims. Other than that, the underlying graph is connected. We don't have any assumptions. Of course, if the underlying graph is connected, then we're not exploring it. Yes?
Are there other problems that have been studied in temporal graphs under this frequency property?
Not that I was able to find in particular. So there's some things called carrier networks, where we have some agents moving around which determine the activation of edges, which has some similarity, especially to temporal edges. This is motivated by problems in maintaining connectivity, so you want to move your agents around so that you can have a good connectivity across the whole graph. These tend to be somewhat under the title of regularity, but they're not fully connected. There's still some gaps, especially to my specific model of frequency.
About the edge periodic temporal graphs that I think have a period on the whole thing.
Yes.
Sure, if there are also some, because this is basically each edge has their own period.
Yes, yeah. What are the results of exploration of these graphs? The thing says more about structure things. I might miss something on that.